Okay, so you've probably all seen electrical outlets, right? In classroom or pretty much at home where you've got. Electrical outlets function, they have these different functions. They're functions of time. One is current. That's the rate at which charge flows through the wires per time. And voltage, you notice electrical outlets will specify a number of voltage. That is specifying EMF or electromotive force. So it's sort of how much electricity is sort of stored there. Resistance, that slows the current down. And inductance is a little bit different. If current is slowing down, it will speed the current back up. But if inductance is, if current is speeding up, it will slow it back down. And that's expressed in this differential equation. The current is equal to the voltage divided by the resistance. So higher resistance means lower current. Higher voltage also means higher current if the resistance is kept constant. We're subtracting the inductance times the derivative of the current. So notice if inductance, say, is some positive constant, if the derivative of the current, if the current is, say, slowing down, that means this is negative, then the inductance is going to increase the current because this term will be positive. If the current is speeding up, the inductance will slow the current back down because this term will be negative. Okay. Now, to solve this differential equation, the derivative of, we can rewrite it in this form. You've seen this form before. So the point here is usually E, the voltage. Voltage might change. Resistance and inductances usually are going to be constants. And this can be a function. So voltage actually could be a function of time. Current is also going to be a function. It just represents how much charge is flowing through one area per unit time. So to solve this, if you notice, we have the derivative of a function with respect to time plus some constant times a function is equal to, this is a function, right? To solve, and even if these things, so usually constants, even if these things, two things were functions of time, we have the tool to solve this equation. The way we solve this equation is by using integrating factors. To solve the equation, how do we use integrating factors? Well, we can just say, all right, the integrating factor, sometimes it's called u of t, it's going to be e to the antiderivative of r over L dt. And then this equation will literally become I times mu of t prime, that just means derivative with respect to time, is equal to e over L. You anti-differentiate, we get I times mu of t is equal to the antiderivative of this function. So here's an example. Let's say the electromotive force, the voltage, is variable and it's given by E naught times cosine omega t. So this is actually an example of voltage that is oscillating. And this does occur when currents happen in nature, they happen in cycles. So voltage could be cycling between, say, high and low values. And let's just say R is 5 ohms, L is 1 Henry. So in that case, what's our differential equation here? The I dt plus R over L times I is equal to E over L. Well, now we can just plug in R is 5, L is 1, and E is E naught, some original constant. Let's actually specify this maybe as, let's say, 10 volts. So that means it's oscillating between 10 volts and minus 10 volts. And we can plug everything in here. So di dt. So again, this is what you would expect, right? If voltage is changing, current's going to change. You would sort of expect that when you flip on a light switch. That means, well, voltage is changing and current changes. Or I guess really what happens then is resistance changes. Resistance goes from being very high to being lower, and that's what allows the current to flow through, say, a cord attached to your computer. Okay. Now, what's our integrating factor? Well, it is literally just e to the antiderivative of 5 dt. Normally this would be r over L. If this is a constant, it would just be the antiderivative of a constant with respect to t. The antiderivative of a constant with respect to the independent variable is just that constant times the independent variable. So this would be e to the 5t. Here we don't have to worry about the integrating constant. So this would be, e to the 5t. And then what does this equation become? It becomes I times e to the 5t prime, remember I is a function of t, is equal to 10 cosine omega t. Omega is just some factor kind of specifying the period of oscillations for the voltage. Now when you anti-differentiate this, what do we end up with? Well, so I'm going to move everything. I'm sorry. So when we specify this integrating factor, it's e to the 5t. We need to multiply both sides by this factor. So I prime. This is a shorthand for derivative with respect to t times e to the 5t is equal to e to the 5t times cosine omega t. This, by the product rule, just becomes e to the 5t times I prime, which is equal to e to the 5t cosine omega t. Now the problem reduces to an integration problem. It reduces to integrating this function, e to the 5t times cosine omega t. Now, to integrate that requires the technique of integration by parts. So I'm going to So to do integration for parts, we need to take the derivative off of one factor and put it on another factor. So it doesn't really matter which one you choose here. Let's just say we pick our factor as being, say, e to the 5t. So we anti-differentiate this, e to the 5t over 5, with cosine omega t alone, and then subtract the integral e to the 5t over 5. Now we need to differentiate this thing. What's the derivative of this? It is negative sine omega t dt. Now notice so now we're actually going to do integration parts one more time. So we have this. Now if we do integration parts to this piece, what do we end up with? E to the 5t over 25 now. I'm sorry, I'm forgetting something. This should have been time minus omega.